right, good morning everyone. I appreciated Wes's talk. I want to talk a little bit about cotton sensitivity to water stress and specifically sensitivity to drought or water deficit stress. So there's a number of different projects that my group has been doing over the past few years, but there's one that I really want to focus on, and it's plant-based irrigation scheduling. So when I was hired here, one of the things that I was expected to do is to evaluate irrigation management and fiber quality in response to irrigation management as well. And so as a physiologist, I'm no engineer. There's a lot of things that I'm not familiar with in terms of irrigation, but one of the things that I know is that one of the best sensors that we can use to tell us when the crop needs to be irrigated is the crop itself. That is, at any given time, water use by the crop is dependent on atmospheric factors, so all of the air temperature, relative humidity, soil characteristics, but then the other thing is the crop itself. So the rooting depth, how large that crop is, in other words, how much leaf area that crop has. So there's a number of things going on all at once that influence whether that crop actually needs water or not. All right? And the water status of that crop is going to be the best indicator of whether it needs to be irrigated. But then what measure do we use? There's all kinds of things that we can use. We can use canopy temperature. We can measure water potential at different times during the day. We can measure stem diameter. There's a number of things out there that are not used currently in production settings, but they're good measures of plant water status. So the first year that I was here, and so in 2012, I had a project where we had essentially dry land and irrigated cotton. This was in 2012, and essentially threw everything that we had at it. All kinds of different measurements, all kinds of different measures of plant water status. And just to kind of let you know what you're looking at here, on the x-axis is Predawn water potential. So this is leaf water potential, Predawn, between 4 and 6 o'clock. And this is net photosynthesis here. Well, the reason I'm showing this is that we could explain about over 94% of the variability in photosynthesis just due to Predawn water potential, which makes sense when it's an irrigation study, right? The only thing we're changing, or should be changing, is water availability to that crop. And so Predawn water potential was really predictive of photosynthesis, so that was good to show that it is affecting the crop itself. But also Predawn, this Predawn part of it, no one necessarily likes going out and getting I'm not saying it's just terribly enjoyable to go out between 4 and 6 in the morning and get these readings in Camilla and then come back to Tifton. But during those hours, I don't have to worry about cloud cover. I don't have to worry, as a researcher, I don't have to worry about all of these environmental parameters that interfere with me getting my measurements. Now, the only thing pretty much that keeps me out of the field is a severe weather event. So the fear of being struck down by lightning, I guess, is the only thing that keeps me out of the field there. So the bottom line is this was to me, from all the data that we collected, this looked like a good indicator. And the idea is if we can use an accurate measure of plant water status to schedule irrigation, then we can see if we can improve efficiency above current methods. All right? If we can't, then we're doing everything we need to do, right? We're being as efficient as we can possibly be, and that's good. We don't need to look at other methods for improving efficiency, right? So what I wanted to do is say, well, how much more efficient? How much can we push this? And so over the past 2 years, so 2013, 2014, there's this study that we've been conducting. It's drip irrigated cotton. This was conducted at the Stripling Irrigation Research Park in Camilla. And there were 2 cultivars. I'm not going to talk about cultivar effects today, though. There were 5 irrigation treatments. So one of them is our extension checkbook recommendation. There are 3 plant-based triggers. These are Predawn water potential thresholds. The negatives throw people off, but this negative 0.5, you'd expect to be more severely stressed than this negative 0.9 here. I'm sorry, you would expect it to be less stressed than the negative 0.9 here. So sometimes it confuses me as well. But anyway, so this is more severe, and then dryland. We didn't irrigate at all. All right, so 3 days a week, water potential was measured, like I say, during pre-dawn hours using the pressure chamber. Essentially, leaves are cut, placed in the chamber, and it's pressurized until water reaches the cut surface of the stem, and that is the water potential of that plant. And what we just to give you a sense, we had 40 plots in this study, and so in less than an hour we could have those 40 plots. We could have water status measured on all of those plots. So this was done 3 days a week. So there's a lot of information here. I want to point out the differences between the 2 years, although you're probably, if you're growing cotton, you probably are aware of the two differences between the 2 years here. So 2013 was a fairly wet year. You see that 66.9 centimeters. I've got everything in centimeters just to give you bearing. That 18 inches that Wes was talking about earlier, that's 46 centimeters. So that year we received 66 in just rainfall alone. 2014 is 34.9 centimeters in rainfall, so drastically different years and different amounts of irrigation by each treatment. So in year one, this negative 0.9, we never crossed that threshold and never irrigated. So anyway, so there's obvious differences year to year and differences in the water applied across all the irrigation treatments. So I feel that I'm somewhat obligated to show this graph just given the amount of work that went into it. This is the Predawn water potential data. So this is 2013 throughout the season. We had a really wet week there where essentially it was just severe weather that entire week. So yes, I did miss some data, but then when I actually was able to get back into the field, you'll notice here we still had some of the highest water potentials. We still hadn't even crossed that threshold at that point. 2014 was drastically different. You can see that the treatments separate out quite a bit. We crossed all of these thresholds at some point during the season. Okay, so if we look at season average Predawn water potential, so if I take the average throughout the entire irrigation period, there's no difference in 2013, but in 2014 there's essentially a stair-step response here to irrigation treatment, all right, with the lowest average water potential throughout the season being the dry land treatment. All right, so let's talk about, so stress, these measures, that's just measures of water potential. That's not telling us how the crop's responding to that water potential. So if you look at plant growth, in 2013, essentially all these lines lie on top of each other. There is no response to irrigation treatment for plant height or main stem node counts. All right. If you look at the different irrigation treatments, you see the dry land down here with the fewest number of nodes. It's also the shortest plants. They actually grouped together here with some of the more, with essentially treatment, the negative 0.7, 0.9, and then the dry land are shorter plants, whereas our well-watered, our checkbook, and our negative 0.5 megapascal treatment, that is, we have taller plants there. They're both about the same in terms of plant growth. Now yield, this is what we're interested in. Last year I've been talking about this for the past, since the last season, or year before last. We had no difference in yield in 2013. We had lots of rainfall, no difference in yield, but significant differences in water use efficiency, which makes sense since we applied less water for each treatment, right? So we had significant differences in water use efficiency. And then I had someone probably in this crowd asking me, well, that's fine, but what would you expect in a really dry year, right? So now I have that information to present for this year. On the right-hand side, we have lint yield here in B. You see B here? All right, so here's our checkbook. Here's the negative 0.5 trigger, and then from there the yields just drop off substantially. All right, so very obvious yield response. In fact, numerically our highest yield was with the negative 0.5 trigger, although it was no different than, not statistically different than the checkbook. All right, if we go over here to water use efficiency, so we matched the yields for the checkbook, and we got the highest water use efficiency. So if I tell you I can improve water use efficiency above the checkbook, but I can't match those yields, that's going to be a tough sell, right? That there's, so I just want to point out we did it. That was also our highest water use efficiency treatment. So does it work? Yes. Now where do we go from here? But let me talk a little bit more about the fiber quality data. Again, 2013. I'm not going to spend much time on fiber quality data for 2014. There's no difference by irrigation treatment. I didn't really. I started these axes at 0, so they don't look like much, but a small difference in fiber quality parameters can mean quite a bit. So anyway, but there was we had significant effects for fiber strength, fiber length. So if you'll look at that red bar there, that's that negative 0.5. We had our longest fibers, again, match the checkbook. If we look at, let's see, uniformity wasn't affected. Micronair, though. You look at micronair, it responded substantially to water availability or to these irrigation treatments, with our more drought stress having higher micronair. All right, you've got shorter fibers, fewer bolls on the plant. During fiber thickening, essentially you just develop thicker fibers that happen to be stronger as well. All right, that's what this data is showing. But again, your yields are substantially lower there. Just to show some regression work, I've shown the 2013 data here. This is just averages by treatment, so this is 8 replicate plots per data point here. You can see this response. You can have too much water, right? So these are the link yields for 2013. You can, let's see, yeah, so there's our 0.5. I'm going to show it on every graph just to point out where it lands on these curves. So this is lint yield. We can explain 97% of variability in lint yield due to Predawn water potential, meaning it worked, right? We can account for that variability by using Predawn water potential. But what about the lowest? So, yeah, those are season averages, but what about the lowest water potential? What this is saying, you really don't want to drop below -0.8 at any point during the season. So once you get above that, like I say, you start to see even just dropping down below that for one day, you see negative impacts on yield. That's what this is showing. All right, and there's our, again, which we already showed that in the other graph. Fiber length, again, there's the -0.5 treatment there. Very strong relationship between fiber length and Predawn water potential. Micronair, so I had to do some fancy curve fitting with this one. I couldn't get many others to fit it very well, but this is a really strong relationship. Essentially, when we have high water potentials, a wet season, we've got really high micronair, and then when we have really drought-stressed plants, we have high micronair as well. All right, in the base, or basically, this is where you want micronair to be, is near the bottom of this curve here. If you look, we have that's our -0.2 megapascal or 5 trigger. So anyway, and then fiber strength again. Fiber strength, our strongest fibers are all actually for the most stress treatments, which again, that's related to micronair, that's related to fiber thickening. All right, so with that, what I want to do is thank the Georgia Cotton Commission for all of their support. I want to thank everyone in my lab for all the help that I've gotten over the past couple of years. And the other thing I want to point out is related to this. Does this mean that you're going to go out and start cutting? Again, if I had a relatively small field, it might not be a big deal. But what I'm looking at is taking this information, and we have canopy temperature sensors. I haven't even shown that data. We have soil moisture sensors. The idea is to correlate that with the soil moisture or canopy temperature data, so that we can optimize. What we've essentially shown is we can improve water use efficiency, maintain high yields, and maintain and keep fiber quality high. All right. So if we can take that information, take it back to something we can do with remote sensing, I think that'll be of value, and that's what we're working on right now. The other thing is the economics associated with this. I'm working with Don Shirley on this project to work out the economics associated with each irrigation treatment. So then I guess you can decide if you'd want to pay for labor associated with that. But again, I think correlating it back to the remote sensors is the way to go. Anyway, any questions?
Is there any chemistry that will reduce plant temperature to mitigate transpiration and loss?
So say again.
Is there any chemistry available to reduce the so that you can mitigate transpiration?
Okay, so that I see what you're saying. Yeah, I don't know of any. Okay, there's all kinds of things that are looked at. There's abscission inhibiting compounds. There's all kinds of things that are currently being looked at under stress. I know that certain fungicides are, essentially there's the argument that they can act as anti-transpirants. So, but then that's different. That's different than what you're saying. You're saying lower that temperature so it decreases the water loss through transpiration, right? Again, I don't know. I don't know of any. And so temperature is another big part of the work that I do. But I'm gonna stop because I'm probably over on time.